Recall that in the last class we learnt Gauss's theorem, which says that the n over p is given by minus 1 raised to m, where m is the number of least positive residues mod p of the first p minus 1 by 2 multiples of n, provided n is not equal to 0. In the course of proving this theorem, we define three sets A, B and C. A and B are the least positive residues mod p of the p minus 1 by 2 multiples of first p minus 1 by 2 multiples of n, and we place them in A or B according as whether they are less than p by 2 or greater than p by 2. And the set C is got from B by subtracting each element of B from P. Now let's go to the next theorem. The next theorem says the following. Let m be the number defined in Gauss's lemma. Then m can be written as the sum of Tn by P plus n minus 1 p square minus 1 by 8 mod 2. Let's come to the proof. Suppose Rt is the least positive residue of Tn mod P. Then I know that Rt can be written as Tn minus P into Tn by P. Now we know that m is the number of least positive residues of n, 2n, 3n and so on up to p minus 1 by 2 which exceed p by 2. And hence, referring to those sets A and B which I just mentioned, I know that R1, R2, up to R p minus 1 by 2 will have all the elements in A and B, that is A1, A2 up to AK and B1, B2 up to Bm. Now, when I add all the elements in this set, we get sum of all the residues is equal to sum of Ai plus sum of Bj. Now, I replace each Rt by its definition. So, I get summation of Ai plus Bj is n into t equal to 1 to p minus 1 by 2 t minus p into summation t equal to 1 to p minus 1 by 2 tn by p. Now, what I do is, I know that Ci is equal to p minus bi. And so, 1, 2, 3 up to p minus 1 by 2, we said in the proof Gauss's theorem that is equal to 1 A1, A2 up to AK and C1, C2, Cm. Now, if I make use of that, I know that summation over t equal to 1 to p minus 1 by 2 of t is equal to Ai plus Cj, and that I can write as summation Ai plus mp minus summation j equal to 1 to m of bj. Now when I rewrite that, mp plus the summation Ai minus summation bj is equal to summation of t. Now when I add these two equations. When I add these two equations, the bj's get cancelled out and I get mp plus 2 times summation of ai from I equal to 1 to k is equal to n plus 1 into r equal to 1 to p minus 1 by 2 of t minus p into summation t equal to 1 to p minus 1 by 2 into tn by p. Now, this I can write as n plus 1 into this summation of t I can write as p squared minus 1 by 2, because this is a sum 1, 2, 3 up to p minus 1 by 2. When I simplify this, I get p squared minus 1 by 8, and here I simplify this, and so I get this expression. Now when I'm going to reduce this modulo 2. When I reduce this modulo 2, I know that n plus 1 is the same as n minus 1 mod 2. and p is congruent to 1 mod 2 because p is a odd number always, and therefore I can replace this n plus 1 by n minus 1, and I can replace this p by 1. So I get n minus 1 p squared minus 1 by 8 plus this summation mod is equal to m. And therefore we've got our result. Now next we come to the quadratic reciprocity law. This is probably one of the most important rules under quadratic residues. Now if p and q are distinct odd primes, then we have p over q into q over p is equal to minus 1 raised to p minus 1 into q minus 1 by 4. Now how do we prove that? By Gauss's lemma and the previous theorem. I know that q over p is minus 1 raised to m, where this is the lemma that we just proved. Similarly, p over q is minus 1 raised to n, where n is, I have a similar expression with a q replacing p. That's it. And s replacing t. Now, hence when I multiply these two, I get minus 1 raised to m plus n. Now look at the function f of xy equal to qx minus py. When x takes the values 1, 2, 3 up to p minus 1 by 2, and y takes the values 1, 2, 3 up to q minus 1 by 2, f of x y takes p minus 1 by 2 into q minus 1 by 2 non-zero values. Now I know that no two of these values are equal, because f of xy minus f of x dash y dash will be equal to, if I put that in here, q of x minus minus py minus qx dash minus py dash. So when I simplify that, I get f of x minus x dash y minus y dash, and that is not equal to 0. For each fixed x, f of xy is greater than 0 if and only if y is less than qx by p, or y is less than this, less than or equal to this, the integer part of that. Hence the total number of positive values is summation x equal to 1 to p minus 1 by 2 qx by p. Similarly, the total number of negative values is summation y equal to 1 to q minus 1 by 2 py by q. Since the total number of positive and negative values together is p minus 1 by 2 into q minus 1 by 2, I can substitute that in this equation, and I get this is equal to p minus 1 by 2 into q minus 1 by 2. Therefore, p over q into q over p is equal to minus 1 raised to p minus 1 by 2 into q minus 1 by 2. Now let me show you how we make use of this theorem. To determine whether 219 is a quadratic residue or non-residue mod 383, we evaluate the Legendre symbol 219 over 383. Now this 219 can be written as 3 into 73, and then I can make use of the multiplicative property of the Legendre symbol to write this as 3 over 383 into 73 over 383. Now 3 over 383 is equal to 383 over 3 into minus 1 raised to 383 minus 1 into 3 minus 1 by 4. This is using quadratic reciprocity. Now I can simplify this. This happens to be 3 can be written as minus 1 mod 4. Minus 1 mod 3, sorry. And therefore this can be written as minus of minus 1 mod 3. This becomes minus 1, of course. This is equal to minus of minus 1 raised to 3 minus 1 by 2 by using congruences and theorem 4, and hence this is equal to 1. Now again similarly I evaluate 73 over 383, which is using quadratic reciprocity I get this. This is equal to, when I reduce it, I get 18 by 73, which is equal to 18. I can use the multiplicative property and write this 2 into 3 squared. So 2 into 3 squared over 73 is 2 into 2 over 73 into 3 squared over 73. 3 squared being a perfect square is always equal to 1 over 73, and therefore this is equal to 2 over 73. Now I make use of the rules that I learnt earlier for 2 over p, and I get this as minus 1 raised to 73 squared minus 1 by 8, which when I simplify I get 1. Therefore, now I can put both these back into this equation and I get 1. Therefore, 219 is a quadratic residue mod 383. One more example. To determine those odd primes p for which 3 is a quadratic residue and those for which it is a non-residue, we evaluate 3 over p. Now using quadratic reciprocity, we get 3 over p is p over 3 into minus 1 raised to p minus 1, 3 minus 1 by 4. Now this is equal to minus 1 raised to p minus 1, this 3 minus 1 becomes 2, so 2 by 4, that 2 cancels and I get minus 1 raised to p minus 1 by 2 into p over 3. Now to determine p over 3, we need to know the value of p mod 3. And to determine minus 1 raised to p minus 1 by 2, we need p mod 4. So we consider p mod 12. Now obviously I know p is odd, so I need to consider only p congruent to 1, 5, 7 or 11, because everything else will give me an even value of p. Case 1. If p is congruent to 1 mod 12, this implies that p is congruent to 1 mod 3 and hence p over 3 is equal to 1 over 3, which is 1. Also p is congruent to 1 mod 4 and hence p minus 1 by 2 is even. Therefore 3 over p is 1. Case 2. If p is congruent to 5 mod 12, this implies that p is congruent to 2 mod 3 and hence p over 3 is equal to 2 over 3, which I can simplify as minus 1. Also I know that p is congruent to 1 mod 4 and therefore p minus 1 by 2 is even. Therefore 3 over p is minus 1. Case 3. If p is congruent to 7 mod 12, then p is congruent to 1 mod 3 and hence p over 3 is 1 over 3, which is 1. Also p is congruent to 3 mod 4 and therefore p minus 1 by 2 is odd. Therefore 3 over p is minus 1. And finally, when p is congruent to 11 mod 12, then we know that p is congruent to 2 mod 3 and hence p over 3 is equal to 2 over 3, which is equal to minus 1 raised to 3 squared minus 1 by 8, which is equal to minus 1. Also p is congruent to 1 mod 4 and hence p minus 1 by 2 is odd. Therefore 3 over p is equal to 1.